Do you know the many surprising connections between the deepest parts of space and the deepest recesses of our ocean? Both are cold, dark places where humans cannot breathe and where the pressure alone is enough to kill you. Both upset our normal experiences of gravity, providing explorers with a strange weightlessness or buoyancy if they could somehow survive being there in the first place. And both contain many unsolved, captivating mysteries. Our oceans are filled with life we've never seen before. And who can say what lurks in the unexplored corners of space? I was initially caught off guard when I heard that NASA had turned its attention towards exploring the hadal zones deep in the ocean. After all, NASA is normally about space. What are they doing deep under the water and on Earth? I'm Alex McColgan and you're watching Astrum. Put on your diving gear and join me in a world of undersea facilities, uncanny life, and an environment so hostile we've mapped more of Mars than of this terrain on our own planet. In 1957, a year before NASA was founded, a paper published by the Journal of the Royal Society of Arts claimed the deep oceans covered over 2/3 of the surface of the world, and yet more is known about the shape and surface of the moon than is known about that of the bottom of the ocean. This was a reference to the fact that in the world before echo sounding technology was commonly used to map the seafloor, we didn't know much about the topography of what was down there. We've come a long way since then, but while we have mapped the moon thanks to satellites and telescopes, we have still only mapped 23.4% of the ocean floor in high resolution. In fairness, this still represents an area of 120 million square kilometers, about 3 times the moon's surface area, so the old saying no longer holds entirely true. Hence why we can instead talk of Mars, which has a surface area of 145 million square kilometers. But still, it's a profound gap in our knowledge of our own world. NASA was founded in 1958 with the purpose of expanding human knowledge of phenomena in the atmosphere and in outer space, and developing vehicles and technologies that would help them to do so. Exploring the ocean was not originally on their radar, or sonar. However, in 1978, NASA began monitoring the ocean with their first dedicated oceanographic satellite, CSAT, which was capable of collecting data on sea surface winds, surface temperatures, wave heights, and other features. This helped them learn more about our planet's oceans and their impact on the global climate. Still, some of NASA's most exciting forays into the ocean only began at the turn of the millennium. One way in which the sea can prepare astronauts for space is through simulated space experiences. About 8.7 kilometers off Key Largo in Florida is the world's only undersea research laboratory, Aquarius Reef Base. Built in 1986, it is a small 3-roomed habitat large enough to house 6 people at a push, with a main room that combines sleeping and living quarters, an entry dock, and a wet porch for entering the sea around it. It was originally designed to help aquanauts remain at the bottom of the sea for weeks at a time through a technique known as saturation diving. By remaining at the depth of 19 meters, the human body becomes saturated with gas dissolved in its bloodstream, which allows these researchers to stay at depth without ill effects for much longer periods of time, 9 hours for one dive rather than 1 or 2 hours. This made it ideal for biologists wanting to study the local environment in situ. In 2001, however, NASA, along with other space agencies such as ESA, realized that it made a great space training location. The cramped living conditions mimic those found on the International Space Station, so astronauts who spent a week at Aquarius Reef Base would get a vital taster of what life would be like up there. It also allowed them to practice performing experiments and generally get used to the expected and unexpected aspects of life in a hostile environment. NASA began the NEMO program, or the NASA Extreme Environment Mission Operations. and that same year began sending their astronauts to the habitat. There have been 23 NEMO missions since then, merging astronaut crews from a variety of different space agencies, which lasted up to 3 weeks. Astronauts there became aquanauts and got the chance to don deep spacesuits, getting a taste for what spacewalks might be like outside of our planet, readying them for the day humans return to the moon or go to Mars. This was not the only use NASA had for the ocean, however. Perhaps the most significant training was not for NASA's astronauts, but rather for the machines that would one day visit the largest oceans outside of planet Earth. Let's now go deeper and consider the exploration of alien oceans. Our solar system is home to many large oceans outside of Earth. Jupiter's moon Europa and Saturn's moon Enceladus, to name just two, have significant bodies of water beneath their kilometer-thick icy surfaces. In spite of only being 1/4 of the Earth's diameter, scientists believe that Europa holds twice as much water as all of our oceans combined. This is an intriguing concept, as even though no sunlight penetrates down to those depths, the mixture of liquid water bordering a rocky inner crust would make both of these locations ideal candidates for life. Scientists have considered how to best test to see if life really has arisen in the oceans of icy moons. In 2024, NASA will launch the Europa Clipper, with the mission to fly by the moon Europa and scan it to learn more about the depth of its icy shell, to try to determine the composition of its oceans and generally get a better picture of the moon as a whole. However, Europa Clipper will only be laying the groundwork for future missions, which one day might see cryobots melting through the 10-kilometer thick icy shell of Europa using nuclear-powered radiators to penetrate its oceans and see firsthand what lies below. Once down there, no radio signal will be able to reach them easily. Messages will be relayed via a vast cable brought down through the ice along with the cryobot. This means that such cryobots will need to be able to autonomously descend a further 100 to 200 kilometers to explore the dark, chilling, and highly pressurized environment they're likely to find, to see what alien life might swim in those waters. So, with a mission objective on the horizon to explore deep, dark waters in search of never before seen life, what better place to start than the unexplored oceans we already have at home? The deepest parts of the oceans on Earth are only 11 kilometers deep, but due to the gravitational differences between Europa and Earth, the pressure you'd experience between the two are much more comparable than you might think. Europa's 100-kilometer deep ocean is thought to have a hydrostatic pressure between 130 to 260 megapascals, which, if it existed in an ocean on Earth, would equate to a depth of around 13 to 26 kilometers. This is much better than if you'd had to go hundreds of kilometers down on Earth, but it's still no picnic. Pressure at the bottom of the Mariana Trench, the deepest place in our ocean, is 1,100 times the pressure on the surface, which is enough to crush the individual cells in the human body, or to implode most submarines. And yet, life survives there, and it doesn't just survive, it thrives. The deep-sea explorers of the Galapagos hydrothermal expedition in 1977, using a specially reinforced remotely operated vehicle that could survive those pressures, were shocked to discover not a barren wasteland, but thriving ecosystems gathered around hydrothermal vents on the ocean floor down there. Tube worms, crabs, and fish were found in rich abundance. As scientists performed more dives, they found all manner of strange life forms down there. Shrimp like amphipods the size of your hand, giant, ethereal, big fin squid that were 8 meters long and looked positively alien. In the depths between 6,000 and 11,000 meters, in an area known as the Hadal Zone, named after the god of the underworld, Hades, life had learned to adapt to conditions in ways no one could have imagined possible. And this incredible adaptability gives scientists a better understanding of what might be possible on other worlds. The deepest parts of the ocean are mostly found near the fault lines of continental plates, where one plate subducts under another. These deep trenches create a unique V-shaped environment that channels organic debris from above down into a sludgy pool. Whenever a carcass falls down there, the organisms in the hadal zone are somehow able to quickly detect it and arrive within minutes. Other organisms rely on nutrient-rich liquids pumped out of thermal vents. If you added up all these trenches into one landmass, you would end up with an area the size of Australia, a whole unexplored continent. NASA wants to explore these regions using autonomous drones, perhaps whole swarms of them that would be able to detect locations of interest such as thermal vents, and would be able to map out the terrain using cameras and onboard AI, similar to that used by the Perseverance rover on Mars. It's a challenging task. Not only would such a drone need to be able to withstand the excessive pressure, but the temperature around such thermal vents can spike to hundreds of degrees. Drones would need to be able to survive rapid temperature swings if they are able to survive. In 2014, one such deep-sea drone known as Nereus was sent into the Kermadec Trench off the coast of New Zealand. This is the area NASA has selected as testing ground for its new equipment. However, sadly, Nereus was not able to survive the pressure down there, in spite of having succeeded on hadal dives before, and it imploded. Pieces of plastic were later found floating to the surface. NASA's latest drone is Nereus's descendant, a smaller, lighter, autonomous submarine known as Orpheus. Orpheus has yet to enter the depths of the hadal zone. Instead, it is being put through its paces in shallower waters. But if it works, its lighter design would make it easier to transport on a rocket to the oceans of Europa at some point in the distant future. Although, this dream might not be so distant after all. In 2023, NASA's Planetary Exploration Science Technology Office gathered a team of 40 top researchers from multiple fields in the California Institute of Technology to discuss how close we might be to making this trip. A surprising amount of technology needed is already there. Their conclusion was that the mission was feasible, scientifically compelling, and the most plausible near-term way to directly search for alien life in situ on an ocean world. With the combined information being gathered by Europa Clipper and the technical experimentation being done with Orpheus and other autonomous submarines like it, perhaps it is something we will see within our lifetimes, although no concrete plans have been made yet. When it finally does happen though, and a human-made drone starts to swim in those dark seas across the gulf of space, what will it see? Perhaps it will feel strangely like home. We are water-based life forms here on Earth. The first large, complex animals formed in our oceans. All life is dependent on water to live. Rather than arid, rocky and dusty wildernesses, there will be something strangely soothing about exploring oceans beyond our own, like entering a place we already know, even though we've never been there before. Does something lurk in those alien seas? Although it's only speculation, the sheer fact that this might be true is enough. To discover that life came to exist not once, but twice in just our own solar system would have massive implications on life's prevalence in the universe as a whole. It would mean life is likely abundant, and we ought to be ready to see a lot more of it out there. But proving it is the challenge. Only by perfecting the technology here on Earth will we be able to crack open those frozen shells, enter those inky depths, and find the definitive answers we seek. For NASA, their mission to find life in our solar system begins in our oceans. Take a walk with me through an ancient, verdant land. So vivid are the colors and aroma of the entangled fauna that it takes you an age to notice something isn't as it should be. It's all quiet. The near absence of birds and mammals is the only indication that this land is dying. Its fate sealed by the ending of an ice age. waters are rising. The lush landscape below your feet will soon be 30 meters below the surface of the Pacific. Any species able to migrate have escaped to continue their fight for survival in a warming, shrinking world. Those given life by their roots are held to perish by them. What is happening here? What can we learn from the history recorded deep in the melting polar ice is of vital importance, because right now, it's happening again. What is causing the ice caps to melt in the present? How will it affect the most powerful climate systems on Earth? And what hidden dangers does the ice contain? I'm Alex McColgan, and you're watching Astrum. Join me today as we look at what makes ice such an interesting and crucial feature of our planet, and imagine a future wetter Earth, one whose existence may have already been forged. On Astrum, we love to explore gigantic objects in our universe whose scale through time and space stretch almost beyond our grasp. Look up towards Cassiopeia, and there is our closest galaxy, Andromeda. 2.5 million light years away, 200,000 light years from edge to edge. Yet, despite its magnitude, we can connect to it. So it's curious to me that looking only 80 years to our future feels too distant to connect with, to understand that things we do today affect tomorrow's world. So, let me take you there. At the beginning of our journey is the ice. Ice is a remarkable substance, one that can store vast amounts of energy. As a comparison, energy stored in modern electric cars, capable of accelerating tons of metal to over 160 kilometers per hour and carry both it and you hundreds of kilometers, could scarcely melt ice that would fit on its back seats. The energy storage capacity of ice is a large part of the reason that the climate has been so stable for the past 12,000 years. The ice is acting as a buffer against extreme temperature rises and falls. The Holocene has been a unique period in Earth's history for another reason too: the rise of human civilizations, made possible through the development of agriculture. The Antarctic ice cap first formed around 37 million years ago. The Arctic 2.7 million, as old as the light reaching us from Andromeda. And both caps are important for our stable climate to this day. Their historical size has largely been defined by Earth's position and tilt in the solar system, movements that affect the amount of energy that our planet receives. These movements are known as Milankovitch cycles, which I have covered in a previous video. According to these cycles, the ice at the poles should be increasing. We should be heading into an ice age. The sea levels should be falling as the ice caps get deeper. But instead, the polar ice is melting. Massive amounts of energy are being absorbed by the caps, and not only are we going in the opposite direction that the Milankovitch cycles predict, the ice loss is accelerating. Should all the ice melt, we are facing a 70-meter sea level rise, which will flood all coastal cities on the planet. Fortunately, that degree of ice loss is exceptionally unlikely, but we do need to know how much sea level rise to expect so that we can plan ahead and protect Earth's ecosystems. To predict just how much, we need to understand why and how the ice is melting. We know the release of greenhouse gases is a driver of today's global warming, overpowering the Milankovitch cycles, causing the ice caps to melt and the sea level to rise. But I was astonished to find out that this hasn't always been the case. Detailed records kept in the Antarctic ice core reveal that in the past, it was increasing temperatures that caused increasing CO2 levels. Cause and effect were flipped. But isn't that a blatant contradiction? Well, actually, no. Each positively influences the other. It's just a case of which happens first. We see this play out as the increased temperatures of today's climate thaw the permafrost around the Arctic Circle, releasing long-stored carbon reserves, which in turn accelerate further global warming. The mechanism by which increased CO2 and temperature affect the polar regions reveals a complicated and fascinating climate system. Greenhouse gases trap infrared heat radiation emitted by the surface of the Earth. This heat is retained by the atmosphere and the ocean. Around 90% of the energy increased is absorbed by the ocean, which is no surprise given it has almost 250 times the atmosphere's mass. So, where does this extra energy go? Well, as anyone who's touched a hot stove or licked a ski lift chair knows, heat moves from hot things to cold things. So it makes sense that it is at the cold poles where we see many times the average global temperature increase, because that's where the temperature gradient demands that the energy flows. And it's flowing there primarily through the ocean currents. Because of its density and heat capacity, water is very effective at transferring energy. That's why water is used both as a coolant in cars and a heating medium in homes, and why air, with a low density and low heat capacity, is often used as an insulator. That difference allows you to sit comfortably in a 90°C sauna for many minutes, while you'd reflexively be unable to insert past your fingertip into water of the same temperature. Other factors play a role in melting the ice too, like the albedo or whiteness of the ice. Soot darkens the surface of the ice, causing it to absorb more energy from the sun. Air quality measures are reducing particulates in the atmosphere and on the ice, meaning we will see less melt from ice directly absorbing the sun's energy. But the lowering of particulates in the atmosphere also blocks less sunlight overall, so more energy reaches the surface, accelerating the greenhouse effect. I told you it's complicated. Let's explore the ways the oceans are melting the polar ice, as it is happening right now on the West Antarctic ice shelf, a particularly vulnerable area. It contains ice in several forms. Sea ice is very seasonal and is responsible for the doubling of Antarctica's area through winter. This ice melts through contact with the ocean as ice cubes do in a cocktail. The direct impact of all the sea ice melting would only contribute a few centimeters to sea level rise, but its importance lies in its role as a barrier to the otherwise exposed ice shelf. The sea ice insulates the oceans from atmospheric warming and keeps the humidity and temperature of the air above it low. Being fresh and white, like the most fairy tale of glistening winter flurries, it also reflects a large portion of sunlight back into space. When this sea ice is low, it exposes the ice shelf, which protrudes almost all the way around the Antarctic. These floating ice shelves can be gigantic. Some, like the Ross and Ronne-Filchner shelves, are greater in area than my home country, the United Kingdom. The warm seawater eats at the underside of the shelves. Huge icebergs the size of our biggest cities can break away as it weakens and drift as far as Africa. Since these ice shelves are melting, they also contribute minimally to the rising sea levels. But it's what the ice shelves hold back that has the most potential for sea level rise. As the shelves shrink, the main body of sheet ice that sits atop land is more exposed, allowing faster flow rates from glaciers and ice streams. But don't be fooled, these ice streams are far bigger than their name would suggest. Incredibly, some are as wide as the mouth of the Amazon, hundreds of kilometers long and kilometers deep, all flowing towards the sea. Feeding these streams is the colossal ice sheet itself. Since the ice sheet is supported on land, the mass of ice melt leads to a direct increase in sea level. These ice melting processes are natural phenomena and would still occur without global warming. The poles take fresh snowfall and ice formation every year, which adds to the mass of the ice. And just for them to retain at their current size, we would witness sea ice melting, ice shelf carving, and glacial flow. Although, at this very moment, Earth's polar ice sheets are far from equilibrium. The The rate at which they are losing ice is quicker than fresh snow can fall, meaning that they are shrinking. Because of the extra energy in our oceans and in the atmosphere captured by greenhouse gases, we are already committed to significant ice sheet loss. Can we say how much sea levels will rise from the melting alone? If you thought it would be a simple case of calculating the volume of ice lost and adding it to the volume of water in the seas, well, you can join me in being wrong. To arrive at an accurate estimate, we need to understand a few other interactions. We tend to think of Earth's crust as solid, but given enough force, the Earth will change shape too. As the ice melts, the continental plate that supports it bears less weight and rises up above sea levels, while at the equator, the coastal land shrinks into the sea, creating localized sea level falls and rises. But the single biggest addition to sea level rise to date required no additional water, and was simply due to the thermal expansion of what was already there. Around half of the sea level rise we have already seen since the Industrial Revolution has been due to this expansion. This process is easy to calculate, and we know how it will contribute to sea level rise in the future. However, the deluge of cold, fresh water being dumped into the salty sea has other, less predictable consequences. Remember, Earth's systems are dynamically intertwined. A feature of these dynamic systems is that they are vulnerable to dramatic changes in behavior, known as tipping points. As with playing Jenga, the tower becomes less and less stable as we mine the lower levels for material to build even higher. Eventually, merely touching the next brick brings it crashing down. This would cause a very rapid phase change. One tipping point that could occur within our lifetime is the slowing of the Atlantic meridional overturning circulation. This is an oceanic flow, a powerful energy transfer system. Should it weaken or collapse completely, sea levels on the eastern seaboard of America could rise by up to 1 meter. But in Europe, coastal waters would recede. However, Europe would face other, more extreme consequences. Around the world, rainfall patterns would change drastically, pushing some ecosystems to become rainforests, while pushing others towards desertification. To understand how all of that is possible, let's look at how the AMOC functions now. The AMOC is part of the thermohaline circulation system. It is driven by changes in heat, thermo, and salt concentration, haline. The AMOC brings warm tropical waters up past the United States and across to Europe, helping to make Northern Europe warmer than it ought to be considering its proximity to the polar circle. As these waters continue north to the Arctic, it is partially frozen into sea ice, which leaves cooler, saltier water to sink to the bottom of the ocean, where it then flows back south to complete the cycle. However, the melting of the Greenland ice sheet is inundating the northern part of the AMOC with fresh water, diluting the seawater, making it less salty and less dense. This makes the gradient directing the water to sink to become shallower, slowing down this part of the cycle and reducing flow, just as a slow middle lane driver on the motorway can cause a tailback, stretching frustratingly far back across all lanes. The slowing down of the AMOC backs up water on the American East Coast and reduces the flow to Europe, meaning that sea levels would rise in America while Europe would be spared, though that's little consolation to a continent that will lose much of its way of life and food production capacity through cooler temperatures. The UK alone is facing an average temperature drop of 10 degrees Celsius, which would make it colder than Iceland now. The melting Greenland ice sheet also contains organisms that we haven't seen on Earth in hundreds of thousands of years. When a new predator travels to an ecosystem not evolved to live with it, it can upset its delicate balance. This is also true of a pathogen traveling through time. Most of the species will be harmless, but as we saw in 2020, it only takes one black swan to change everything. With more cells being released from ice melt each year than there are grains of sand on Earth, the risk one is a black swan is significant. A risk that increases with the depth with the permafrost thaw. The further back in time a potential pathogen is from, the bigger the jump in its genome and the lower our ecosystem's readiness for it. So, the world is changing. As we have seen, ice is an incredible recorder of Earth's history. Through studying its secrets, we can see Earth's past. Just as the ice cores detail Earth's ecosystem as the Bering Strait flooded, it contains our history too. As the ice melts, it replays many of humanity's environmental missteps by re-releasing trapped chemicals we have produced. CFCs stored in the ice can again deplete the ozone and accelerate Arctic ice loss. Chlorinated pesticides, many long banned from use, can find their way back into Earth's ecosystem, some of which will have been made even more potent by their time stored in ice. Vaporized lead from the use of leaded petrol will also be re-released as the ice layers that contain it melt away. This chemical cocktail adds yet more stress to a global ecosystem moving ever closer to an invisible edge. When we add all these factors together, the year 2100 could look very different. Exactly how different is under our control. The current predicted average sea level rise is 0.5 meters. That doesn't sound like much, does it? A map of the world's coastlines would look almost unchanged. However, it's not the averages, but the black swan events. The storms, the floods, the heat waves that drive human behavior. By the year 2100, a population the size of the US will be exposed to regular coastal floods. Faced with increased risk, where will Earth's coastal populations move to? How much will our way of life change? The rich diversity we see in cultures and species on Earth is born out of adapting to the environment. Both humanity and life itself have demonstrated time and time again that they are irrepressibly adaptive. Humanity can and has to learn from its past and look to the future. So there is hope. While the melting ice reminds us of the environmental damage we have been responsible for since the Industrial Revolution, it also reminds us of how often we came together to make a change for the better when we understood how we were affecting our planet and ourselves. I believe we can and need to do it again. Above our planet's poles, an invisible force is at work. Hypothesized decades before we were able to measure it directly, this global energy force is responsible for sculpting our atmosphere and driving charged particles into space. It's also why some planets end up uninhabitable altogether. It's called the ambipolar field, and it's a force as fundamental to our Earth as gravity or magnetic fields. Although, for the sake of life on Earth, it's a good thing it isn't too strong. Recent breakthroughs from NASA's Endurance mission have finally allowed scientists to solve a 60-year-old mystery by measuring the ambipolar field for the first time, proving once and for all that our planet has a third global energy field. I'm McColgan and you're watching Astrum. Join me today as we unravel the mystery of our planet's ambipolar electric field, a phenomenon that not only powers the polar wind, but also has an enormous impact on our planet's habitability. Earth's magnetic field, depicted in this video as onion-like layers of lines, helps to shield our atmosphere from dangerous solar energy and damaging cosmic rays. And the gravitational field, shown here as the white glow around our planet, not only keeps us planted on Earth's surface and stops our atmosphere from drifting away, but also provides valuable information in the study of Earth's changing climate, sea level rise, ocean circulation, and much more. As you can see, our magnetic and gravity fields are critical features that help make our planet habitable. And with the recent publication of a 2024 paper in the journal Nature, direct evidence has been found for a third energy field, the ambipolar field. To understand this energy field, we need to talk about plasma. Like a solid, liquid, or gas, plasma is another state of matter, which happens to make up 99% of all visible matter in the universe. Plasma is made of ionized particles and is responsible for several well-known phenomena on Earth like the aurora borealis and lightning. Plasma can form where atmospheric gas density becomes low enough to support the conditions for it, and around 90 kilometers above Earth's surface. This plasma is made up of very lightweight, fast-moving particles which get trapped along the Earth's magnetic field lines as they move away from the surface. Around the majority of our planet, plasma encounters a barrier that limits its escape into space, known as the plasma pores. Here, plasma co-rotates along with Earth along its closed magnetic field lines. Until the mid-1960s, the prevailing model of our planet's magnetic field theorized that all of the magnetic field lines were closed and the plasma remained trapped. So what changed? We went to space. In the 1960s, the first spacecraft flying over our planet's north and south poles could actually detect a supersonic wind of charged particles, or plasma, flowing out to space, including positively charged hydrogen and oxygen ions. This observation led scientists to start wondering whether the Earth's magnetic field model should have an open rather than a closed tail. At the time, scientists already knew that our atmosphere lost some particles to space due to thermal escape. This is a type of atmospheric escape that typically happens when the energy from sunlight heats up particles in our atmosphere, allowing them to reach escape velocity and break free of our planet's gravitational pull, kind of like when a pot of water boils and steam evaporates. So it was no surprise that some particles would be escaping into space, but something didn't quite add up. If energy from the sun were the only cause of atmospheric escape, one would expect the particles that were escaping into space to be heated. However, many in the stream were actually cold, with no signs of being heated, and yet they were traveling at supersonic speeds. Scientists hypothesized that there must be another invisible force driving this phenomenon, and in 1968 the term polar wind was coined to describe it, leading to more research and theories into its cause and effects. The idea of a planet-wide electric field was developed to explain the polar wind, but when this was theorized in the 1960s, it was thought that the force was too weak to detect. And at the time, scientists were correct. The electric potential was so weak, it would require very sensitive instruments to measure, and that technology wouldn't be invented for several more decades. Enthusiasm to measure our planet's ambipolar field was spurred again in 2016, after a clue came from the European Space Agency's Venus Express mission. One of the reasons that Earth is hospitable for life is because of its water, while Venus today is dry and barren. However, billions of years ago, evidence suggests that Venus might have had abundant water like our own world does now. This raises the intriguing question: if Venus once had water, where did it all go? The ESA's Venus Express mission offered a potential explanation when it detected a 10-volt electric potential around Venus, at least 5 times larger than expected. This marked the first successful measurement of an electric field on any planet, including Earth. The electric field surrounding Venus could pull positively charged ions like oxygen out of the atmosphere, draining it of the essential ingredients of water, like a vacuum cleaner siphoning particles out to space. Over time, this could have played a role in draining the planet of its once abundant water. This prompted a question much closer to home. Does Earth have a similar electric field? And if so, why has our planet managed to hold onto its water? The electric potential measured around Venus was around 10 volts. For comparison, a standard car battery is 12 volts, but scientists expected our planet's electric potential to be as little as 0.3 volts, similar to a button battery you might find in a watch, and some 25 times weaker than the electric potential on Venus. It's this difference that may be a key reason why our Earth has been able to keep its water. And that's what inspired NASA's endurance team to develop a new type of scientific instrument called a photoelectron spectrometer to find Earth's weak electric field. The instrument is designed to measure the speed of electrons escaping from Earth's atmosphere as a way to reveal our planet's electric potential. Earlier, I explained thermal escape, and I mentioned that particles are able to escape from our atmosphere when they reach escape velocity. That escape velocity is a very specific, predictable speed, but this speed should be ever so slightly slowed by Earth's electric potential. And so, by measuring that slowing effect at apogee, or the furthest point in Endurance's orbit from Earth, the instrument would be able to measure the strength of the electric potential around our planet. Such a sensitive instrument would need to be launched at precisely the right location and time in order to ensure a chance at making the observation successful. The Svalbard rocket range was selected for the job. It's the northernmost range in the world, located in Svalbard, Norway, a group of islands in the Arctic Ocean. Here, the NASA Endurance team would be able to launch the instrument on a suborbital rocket through Earth's magnetic North Pole. And on the 11th of May 2022, the team of international scientists did just that. Named after the ship that carried Ernest Shackleton's crew in their 1914 attempt to reach the South Pole and cross Antarctica, the Endurance mission launched its suborbital rocket to an altitude of 768 kilometers, collecting data over 518 of those kilometers before splashing down 19 minutes later in the Greenland Sea. During its flight, the instrument measured a change of 0.55 volts in electric potential between 250 kilometers and 768 kilometers. Space scientist Glenn Collinson, the principal investigator for NASA's Endurance mission, said even though half a volt is almost nothing, again almost about the strength of a watch battery, it's just the right amount to explain Earth's polar wind. This first ever direct measurement of Earth's electric field marked a pivotal moment in our understanding of this fundamental planet-wide energy force. The ambipolar field exists in what's called the ionosphere, a region that stretches across 3 out of 5 of our atmospheric layers. Our atmosphere is divided into 5 main layers. The troposphere, also known as the lower atmosphere, only reaches about 20 kilometers above Earth's surface and is where the majority of weather occurs. Next is the stratosphere, which extends up to about 50 kilometers and contains most of our planet's ozone that protects us from ultraviolet radiation from the sun. This layer has very little circulation and is where commercial airlines usually fly. Above the stratosphere is the mesosphere, extending up to about 85 kilometers. This is where meteors burn up near the bottom of the mesosphere layer are thick enough to slow them down. It's within the upper reaches of the mesosphere that the ionosphere begins, but its influence stretches far beyond that. Starting around 80 kilometers above the surface in the mesosphere, the ionosphere continues outward through the entire thermosphere layer from about 85 to 600 kilometers. This is where auroras happen, and high-energy ultraviolet and X-ray radiation are absorbed, creating charged particles. And finally, the ionosphere ends in the lower exosphere, which begins around 600 kilometers and continues out to about 10,000 kilometers from Earth's surface, where it fades into outer space. The exosphere is where many satellites orbit around our planet. As you can see, the ionosphere starts around 80 kilometers above sea level and stretches hundreds of kilometers into space, where it overlaps with Earth's magnetosphere, a region of space surrounding Earth. Within this massive region of the ionosphere is where we find the ambipolar field, which is theorized to begin at around 250 kilometers. While most of our atmosphere is composed of nitrogen, the upper region of our ionosphere is home to lighter elements like oxygen, hydrogen, and helium. When photons from the sun collide with these elements in the upper atmosphere, they can knock electrons loose from the elements in a process called ionization, leaving positively charged particles called ions and negatively charged electrons. Because of the opposite charges of the negative electrons and positive ions, they are attracted to each other and become tethered together by an electric field. It's this electric field that constitutes a major part of the ambipolar field. The electrons within the electric field are so light that the slightest push could send them flying out to space, while the ions are more than 1,800 times heavier than the electrons and sink toward the ground due to gravity. The subatomic tug of war works in both directions, but the upward tug from the energized electrons is able to just slightly overwhelm the force of gravity on the ions. This outward pressure of ionospheric electrons is what creates the ambipolar field, depicted here as the sparkling blue glow around our planet. The upward lift inflates our planet's ionosphere and accelerates some ions enough to escape from the atmosphere, creating the polar wind along our poles' magnetic field lines. What's more, the ambipolar field can achieve this acceleration of plasmas without heating them, providing an explanation for the cold plasma scientists had detected escaping from the ionosphere. It's the bidirectional nature of the interaction between ions and electrons that gives the ambipolar field its name. The Latin prefix ambi means both, and polar refers to the polar regions, where the electric field's effects are felt the strongest. Collinson, the Endurance mission's primary investigator, called the ambipolar field an agent of chaos, stripping particles from our atmosphere away into space. Hydrogen ions make up the majority of the polar wind. They are so light, the ambipolar field's upward force of these electron ions is 10.6 times stronger than the force of gravity, leading the ions to accelerate up at supersonic speeds and escape from our atmosphere above the Earth's magnetic poles. Scientists have found that our planet loses about 3 kilograms of hydrogen gas every second, or 95,000 tons per year. Additionally, the Earth also loses about 50 grams of helium per second, or 1,600 tons of helium gas per year, a smaller but still measurable amount, and a much smaller amount of other gases like oxygen. However, not all of this is due to polar winds. It occurs through a combination of factors, including thermal escape and non-thermal escape mechanisms such as polar wind. But don't worry. Despite our planet losing several thousand tons of its atmosphere to space every day, we are nowhere near running out of air. The planet won't run out of oxygen for 1 billion years. It will be another billion years after that before our oceans will have been depleted of most of their hydrogen. Around 4 billion years from now, our planet may look very similar to how Venus looks now. All of our water will have evaporated, and the greenhouse effect will have become strong enough to melt rock, leaving our planet a dry, lifeless world. Keep in mind that modern humans have only existed on this planet for around 300,000 years. Our species would need to exist more than 3,300 times that length to be around in 1 billion years. While not really important on human timescales, it is still interesting to think about though. And while hydrogen ions may be the lightest and most common type of ion to escape in a polar wind, heavier particles also get a boost from the ambipolar electric field, helping to shape our atmosphere's structure and dynamics. How exactly? Well, now that we've measured the ambipolar field, scientists can delve into all the ways the ambipolar field shapes our atmosphere. Take oxygen ions for example. These heavy ions weigh half as much when they're immersed in the 0.55 volt ambipolar field. This effect increases the ionosphere's scale height by 271% which means our atmosphere can remain denser at greater heights than it would otherwise be able to. Endurance's discovery and measurement of the ambipolar field also provided an important key to understanding why Earth has been able to hold on to much of its water up until this point, while our neighbouring planet Venus was not able to do the same. It's theorized that any planet with an atmosphere may also have an electric field, and you may recall that earlier I said Venus's electric potential was measured to be around 10 volts, roughly 18 times stronger than the ambipolar field on our own planet. While Earth does lose a constant flow of particles to space, both through the polar wind as well as other types of atmospheric escape, this effect would have likely been much more pronounced on Venus because of its stronger electric potential, leading to the loss of heavier particles like the ones that make up water. The fact that our ambipolar field is so weak may be an important part of why our planet has been able to hold onto its water. We've only just started to explore the depths of how the ambipolar field has influenced our planet and life on Earth, and the Endurance scientists have said there are already plans for additional measurements of our planet's ambipolar field in the future. Like its predecessor, the new rocket will also carry the legacy of a long-past Arctic explorer, named after the Resolute, a ship that set off to explore the Arctic in 1850. And now that we've finally been able to confirm and measure the ambipolar field strength, and with a follow-up mission already planned to take more measurements, scientists can start asking some of the bigger and more exciting questions, like what it means for Earth's complex atmospheric dynamics, and how it helps to govern planetary evolution. And doesn't the potential insights we stand to gain from this research feel electric?
NASA's Mars Reconnaissance Orbiter has been imaging the surface of Mars for over 10 years now, with its powerful high-rise camera. 10 years of taking photos every day means that its catalogue is huge, and we can pick out pretty much any part of Mars that we want to have a closer look at. Today, I thought it would be really interesting to investigate the sand dunes on Mars and see how they compare to the wonderful sand dunes we have on Earth. You may have already seen imagery of the Sahara Desert, with dunes hundreds of meters tall, or the Namib Desert with rolling sand dunes as far as the eye can see. Did you know though that there are 5 different types of sand dunes, and that Mars has a type of dune Earth doesn't have? And also, what are the biggest dunes on Mars? The most common type of sand dune on Earth is the crescent or the Barkhan sand dune. While not always as distinctive as these dunes in this image, they are plentiful and found in most sand deserts. They are defined by this kind of crescent shape with arms, and they are usually wider than they are long, like you can see here. They form like this because in these places there is only one dominant wind direction. They have a shallow slope on one side that faces the wind and a slip face on the other side. They are a type of transverse dune, as they move gradually over time as the wind blows, whipping sand from the front, over the top and down the slip face. When many of them merge, they can create an almost wave of sand, smooth on the side facing the wind, with a slip face away from the wind, moving gradually over time with the wind's direction. They are also in plentiful supply on Mars. All of the ones I'm about to show you can be found at the base of various large craters. Going to this old crater near Mars's equator, Barkhan dunes can be seen lumped together somewhat here in this plane. This happens when there is a plentiful amount of sand and the dunes merge together into a big lumpy transverse dune. But individual dunes are really evident a bit higher up, where the sand is contrasted against the bedrock. Here are some more found in Arkhangelski crater. When there is a smaller amount of sand, the dunes tend to stay separate, which looks really peculiar from above. These dunes do move, although very slowly. Here's a couple of examples of dunes on Mars, moving slowly over the course of 2 to 3 years. Scientists originally thought that sand dunes would stay pretty motionless on Mars, as sand dunes require wind to move them, and Mars only has about 1% of the atmospheric pressure at the surface compared to Earth, whose winds can easily move sand. We knew the wind on Mars could pick up tiny dust particles, but it would require extremely strong winds to move sand. This could be helped though by the fact that sand on Mars is not exactly the same as Earth's sand. In my Opportunity video, I mentioned that the sand particles Opportunity analysed were far smaller than what we're used to on Earth, which may aid the movement of these dunes. But what happens if the wind is bidirectional? Going back to Earth, a beautiful type of dune which can easily be seen all the way from the International Space Station is the longitudinal or seif dune. Seif is the Arabic word for sword, which describes these dunes nicely as they are long and narrow. These linear dunes can be hundreds of kilometers long and are often found in parallel sets, separated by gravel or rocky corridors. These occur where wind directions can flip over, meaning that these ridges have a slip face on either side of the dune, making them appear quite sharp. Seif dunes also appear on Mars, and in my opinion, the most beautiful example of it can be found here. Again found at the bottom of a crater, these dunes look remarkably similar to each other, including this dusty band found on each one. Although we're not totally sure how they form, one leading theory is that they are the result of wind directions changing around Barkhan dunes. In this image, some Barkhan dunes seem to be mid-process of forming into seif dunes. It's a really pretty image that seemingly tells a story. To our right here, we have a mesa being eroded, feeding sand into the valley below. Then you have these beautiful examples of Barkhan dunes, which show the step-by-step process of becoming seif dunes. Another spectacular example of this, a bit further into the process, can be found here. The contrasts of the different materials in the image are stunning. And the dark sections are the sand dunes merging together. The third type of dune is the dome dune. Typically, these are not very big on Earth, usually only a few feet high. They have no slip face, they are smooth all over, hence the name. They are quite rare, and usually found in and around other types of dunes. And yes, these are also found on Mars. Here's a field full of domes, a few of which can be seen starting to cross over into Barkhan dunes. And in this impressive expanse of dunes, and I really do mean an expanse as these dunes continue on way beyond this image. You have wobbly lines of dunes with domes on the end of them. These domes seem to be much bigger here than they are on Earth. The domes here tens of meters across. This field is indicative of a change in wind direction, as the lines are nowhere near as straight as in some of these previous images. The fourth type of dune is a parabolic dune, which is the opposite of a Barkhan dune, meaning the slip face is on the other side compared to a Barkhan dune. These occur near coastal regions and form the way they do because something, often vegetation, anchors the arms of the dune in place. Lack of vegetation on Mars means it's a bit tricky to find parabolic dunes. The closest thing I found is this beautiful image, a dune wrapped around a large mound in the middle. The dune is clearly moving from left to right in this image, and you can even see the shadow of the slip face just by here on this side. The existence of this dune is heavily influenced by the size and shape of this mound, funneling wind along its walls. The fifth and last type of dune is the biggest type, the star dune. This is a dune where wind direction changes frequently, meaning the dunes in this region have 3 or more arms and are often stationary, just building up over time. This impressive image is the Sahara Desert as seen from the ISS, and it is full of star dunes. The scale of these dunes truly is impressive. Zooming in, you'll realize that these dots are people. And of course we have star dunes on Mars. Some are small, a collection of dunes merged together, but others are massive, like these found in Russell Crater, which reach far beyond this image. As this image is found nearer the poles, carbon dioxide ice can form on these dunes. During the Martian spring, the carbon dioxide sublimates, which dislodges loose material, leaving these streaks. Moving to another image, again near Mars's pole, we find one of the most beautiful images of Mars I have ever seen. This image was taken just as the sun was either rising or setting, meaning a lot of the image is shadows cast by dunes. I love this as it provides a sense of depth to the image. These again are big star dunes, with their individual arms reaching out for kilometers. There's one last thing I want to talk about the dunes of Mars. Have you ever been to the beach and seen sand ripples like these? These are actually a type of transverse dune, forming perpendicular to the direction of the water waves as they flow over the sand. Much like larger scale transverse dunes caused by the wind. Mars has these ripples too, but they are much bigger than what you would find on Earth, with a meter or 2 between the ripples. This size makes it difficult to see from space, but luckily we have another rover on hand, Curiosity, seen here in this image, to take this remarkable photo of them. Scientists didn't even know this type of dune existed, and it is a fitting reminder that although Mars may appear quite familiar to us, it is still a world full of secrets and unexplored facts, and there is still so much we can learn from it.
Thanks for watching. Making this video required some long-term planning and work, which we were only able to do thanks to the consistency and sustainability of your memberships as Astronauts on Patreon. A huge thank you to everyone who has signed up, and if you'd like us to make more videos like this, you can join with the link down below. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.